Recall that in our parent function and transformation unit, we talked about the fact that 2 to the x and log base 2 of x are inverse functions of each other. We looked at their graphs and we saw that, for example, this graph of 2 to the x has an asymptote on the x-axis and then it moves up. The log base 2 of x has an asymptote on the y-axis and is shaped like this. If we could put them two together on one grid, we would have 2 to the x and log base 2 of x, and you could see that those two graphs reflect across the line y equals x, showing that they are inverse functions. Now another thing we talked about with inverse functions, if I do f of f inverse of x, I should get x. So let's do that. If I take the entire log function and put it in as an input into the exponential function, it would replace the exponent. So I would have 2 to the log base 2 of x. That equals x. This is an important relationship. Notice that the base of the exponent and the base of the log match, and these two numbers are the same. An example of this would be 2 to the log base 2 of 8 equals 8, because log base 2 of 8 equals 3, 2 to the third equals 8, so 2 to the third equals 8. And this will be true no matter what those values of x are, as long as the two bases match. So those two bases could actually be any number as long as they're the same base. What if I do the other way around? I'll get another interesting relationship. If I substitute 2 to the x in for x in the log function, I get log base 2 of 2 to the x equals x. Well, that makes a little more obvious sense, because if I do 2 raised to the x power, I should get 2 to the x. So an example of that was something we saw in one of our notes questions a little while ago, was log base 5 of 5 to the 7th equals 7. So once again, if the two bases match, the exponent here matches the number on the other side of the log, which is also an exponent, because remember, a log equals an exponent. So there's a little something about them being inverse functions. Now the other thing I want you to see is some interesting properties of logs, and to do this we're going to be looking at some things on the calculator. So I'm going to be writing down a few logs here, and I want you to leave a little space before this one and then a space in between them, just like I'm doing. Okay, actually I want to leave a little bit more space at the end down here. Okay, log point of 0.01. Okay. So I'd like to get those where they all fit on the page at the same time. Okay, there we go. Now, on your calculator, I wanted to show you that if you're using your calculator, let me see if I can move this screen so it fits the calculator screen a little better. There we go. If you look over here, you'll see a button that says 10 to the x power, and above it is log, and e to the x, and that's natural log, ln. So we're going to use those a lot. So if you do control 10 to the x, you get log. Now, let's put in 100 for the input of the log, but not put in the base. If you push enter, notice it automatically fills in 10 as the base. That is the common log, so if you don't put anything, it'll automatically put 10. What if we wanted to use a different base? We could do log base 2 of 8 and get, it's kind of my go-to example, get 3, okay? Now, what we want to look at is, in a little bit, is what happens when we take the log of something that doesn't give us a nice number. So we're going to start out with some nice numbers. So what I'd like you to do, and this is something nice about your calculator too, is you can highlight something, push enter, and it copies it back down, and then you can go back and edit it. So I'm going to make log base 10 of 10, which is 1, and then I want to do log base 10 of 1, which is 0. Now what about log base 10 of 0.1? 0.1. That's not what we've seen before. That's -1. Why is that -1? Well, that's -1 because 0.1 is equal to 1 over 10, and we know that 1 over 10 is 10 to the negative 1 power. So 10 to the negative 1 power is 0.1. If I go up and grab, okay, I think I have to erase this off here to, okay, so if I go up here and grab this again and then change this to 0.01, notice that is negative 2 because 0.01 is the same as 1 over 100. And I know that 1 over 100 is 1 over 10 squared, which is the same thing as 10 to the negative 2 power. So that's where we get the negative 2 there. So going back to the notes here, let's write down some of this. So I'm going to kind of shift this up here a little bit. So we have log base 10 of 100 is 2, log base 10 of 10 is 1, log base 10 of 1 is 0, log base 10 of 0.1 is negative 1, and this is negative 2. So if you want to kind of write over to the side, that's because of, so for example here, this is because that 0.01 is 1 over 100. 1 over 100 is equal to 1 over 10 squared, which is the same thing as 10 to the negative 2 power. So this is the same as 0.1 is equal to 1 over 10, which is 10 to the negative 1 power. And remember that 10 to the 0 equals 1, and so forth. I think you know the other ones. All right. Now, without using your calculator, you might want to pause the video for just a second and try to figure out what is, and I'm going to put this in a different color, I think. So let me try to get my little backwards button to work, but it's sort of hiding. Okay, so what is log of 25? So you might think about, pause the video and think about that for a minute. Students guess all kinds of different things about that. Some of them think it's not possible because there is no power of 10 that would give us 25. Some people think it's some sort of a fractional power. There's all kinds of things. But here's, I want to point out something to you. 25 is a number between 10 and 100. So it's the exponent that we put on 10 to get 25 should be a number between 1 and 2, because 10 squared is 100, 10 to the first is 10. So 10 to some power between 1 and 2 should give me 25. So this is one where we're going to want to check this out on the calculator. Oops, I hit the wrong button here. Calculator button. There we go. So I'm going to erase this off again here. And I think I'm going to clear this kind of to start over so we can see this better. So do my log again. So log base 10 of 25, so I don't have to put... Now, if you just push enter here, you get 2 times log base 10 of 5. And we'll talk more about that later, why you get that. But what I'd like you to do is do a control enter. And you get 1.39794. And I'm just going to do the first 4 digits, 1.3979. And that is a number between 1 and 2. So we're saying 10 to the 1.3979 is equal to 29, or is equal to 25. What about this one? Log of 4. Well, now you're going, oh, I get it. That's going to be a number between 0 and 1. And you are correct. That is a number between 0 and 1. So let's take a look and see. You might have a guess of that. You probably have no idea really what that number is. So if I do this, log base 10 of 4. Once again, if you do this again, you'll get 2 log base 10 of 2. But we're going to do a control enter. You get 0.60206. I'm going to round that to 0.6021. 0.6021. Okay, I'm going to do another one. Log of 0.4. So I have log of 1, log of negative 1, so that this number has to be a number between 0 and negative 1. Any thoughts? What could it be? Shoot, I wanted to put that in blue. I'm trying to keep a trend here to make my notes look nice. So this is log of 0.4 equals. So let's check that one out. And I'm going to do that by copying and pasting the one I just did. Shoot, you can't see that very well with my screen. Okay, so change that to 0.4. And you get, ooh, negative 0.39794. Okay, so this is negative 0.3979. So we saw that number already before. So what happens with log of 0.04? What's that going to end up being? Let's check that one out. So I'm going to go up and copy this, edit it, Control Enter. Oh, negative 1.39794. That's interesting. Negative 1.3979. Okay, so log of 25 is positive 1.3979, and log of 0.04 is negative. I don't know that we would have seen that one coming. Well, let me show you some relationships that might explain some of what we're seeing here. I know that 4 times 25, and actually I'm going to spread this out more. You might want to spread this out more too. 4 times 25 equals 100. Now I'm going to write each of those numbers as a power of 10. So we know that 100 is 10 squared. That was written very oddly. Let me try that again. It's 10 squared. I know that 25, now you might not think of this, but remember, I know that 10 to the second power is 100. 10 to the 1.3979 power equals 29. So I can write this as 10 to the 1.3979 power. And 4 I can write as 10 to the 0.6021 power. 10 to the 0.6021 power. Now notice we have two numbers with the same base that we are multiplying together. That means we can add their exponents. So I should be able to say 10 to the 0.6021 plus 1.3979 equals 10 squared. Well, if you look carefully at 0.6021 and add that to 1.3979, so 0.6021 plus 1.3979 equals 2. Okay, so the exponents add. Just should not be a shock, but it's just a weird one to see. Okay, so we can add exponents. So let's think about adding exponents. We added 0.6021 plus 1.3979, and we got 2. Well, if you go back and look over here, we see that 2 is equal to log of 100, 1.3979 is equal to log of 25, and 0.6021 is equal to log of 4. So I could write this as log of 4 plus log of 25 is equal to log of 100. So notice when I add two logs, I'm adding, it equals the log of the product of those two things that are inside the log. Why can I add logs? Because logs are exponents. When I'm adding logs, I'm adding exponents. I'm adding the exponents that give me the the exponents that when put on 10, in this case, give me 4, 25, and 100. So in general, we have a principle that says log of x plus log of y is equal to log of x times y. So there is a principle that we can use when we are doing things with logs. You can see this with several other examples. If we were to do a couple of others, just kind of look at these. So how do we get 0.4? Well, we would multiply 4 times 0.1. Okay, so let's try that one. So if we multiply, and I'll get where I can see both of those numbers. So if we do 4 times 0.1, we get 0.4. Well, 4 is 10 to the 0.6021 0.1 is 10 to the negative 1, and 0.4 is 10 to the negative 0.3979. So notice if I add up 0.6021 minus 1, I would get negative 0.3979. Okay, so the same thing works. It's also true that if I want to divide two numbers, I would subtract the logs, because I could also think of 4 divided by 10 is equal to 0.4. And so I could think of this as 10 to the 0.6021 divided by 10 to the first, and I would subtract the exponents, and I would get 10 to the negative 0.3979. So it's also true that log of x minus log of y is equal to log of x over y. So that's another thing that we can do with logs. So we'll look at some more interesting log properties as we go. So just to end, okay, so looking at all of our logs that we have here, can you figure out, without using your calculator, how to get log of 400? How do you get log of 400? Pause and see if you can figure it out. Okay, 400 is 4 times 100. So I could say 10 to the 0.6021, that's 4, times 10 to the second, which is 400, and I'd add those exponents. So what I end up with is, hey, I can just turn that from a question mark into a 2, 2.6021. I would add those exponents there. So there's some interesting things about logs for you to ponder.